Okay, welcome back, class. In this video, we're going to be exploring what would have been the last objective of Unit 5, and that is to evaluate integrals algebraically involving composite functions using U substitution. So that U substitution is going to be really important today in understanding how to evaluate integrals. And so what is U substitution? Well, U substitution is simply a technique that allows you to evaluate integrals involving composite functions. So up till now, we've been working with polynomial functions, even trig functions. But now we are going to be looking at functions, both polynomial and trig, square root functions, log functions. But now it's going to be composites that we're dealing with. So what this usually means is that finding the antiderivative is just a little bit more complicated, and sometimes it's not able to be done mentally. And so the U substitution method is going to help us when those things happen. There's a couple things we need to remember before we get started with examples. The first one is the fundamental theorem of calculus part 2, which says that to evaluate a definite integral, an integral from a to b of f of x dx, we need to take the antiderivative of b minus the antiderivative of a. There's also one more thing that I didn't quite cover in class that I'd like to point out right now. And I'm not really going to explain the reason why, because we're not ready for that explanation yet. But I will refer back to this moment and explain it in a later lesson. And that is this. If you take the integral from a to b of 1 over x dx, the rule that we have, the shortcut rule that we normally use, doesn't work in this case. You see, if we bring x to the top, we write it as x to the negative 1, and we try to apply that rule where or the little shortcut where you add 1 and multiply by the reciprocal, what you end up getting is x to the 0. And then if you multiply by the reciprocal of 0, well, that's 1 over 0, so that's bad news. That's definitely not the antiderivative of 1 over x. So that system is going to be bad. It's not going to work for this particular function. And so you basically have to go back and think 1 over x. What would give me the derivative as 1 over x? And if you go back to derivatives of logs, you will remember that the derivative of natural log is 1 over x. So the antiderivative of 1 over x is going to be natural log, but it's not just going to be x, it's going to be the absolute value of x. And that's going to be from a to b. I'll try to explain this absolute value here in just a moment. But anytime you take the antiderivative of 1 over x, it's going to be natural log, and you must include absolute value around the x. And so you would finish that with natural log of b minus natural log of a. And I'll explain this more in the future, but basically if you look at the original function 1 over x, its domain is all numbers except 0. That means you should be able to put in negatives and you should be able to put in positives, just not 0. Well, when you take the antiderivative's domain should match the domain of your function. So natural log, its normal domain, if it's just natural log, is from 0 to infinity, which means you cannot put negatives. But your original function says you can, your integrand. So you would have to put absolute value signs around it so that positives and negatives are allowed. You still can't put 0. That's okay though, because you weren't allowed to put 0 in the original one anyway. So those are a couple things to keep in mind as we move forward with U substitution. Okay, so I'm going to go ahead and set up my problems. We're going to do 4 examples. So that you better understand how this is going to work. So here I have my first example. It's the integral from 0 to pi halves of cosine of 3x dx. Now this particular problem involves a composite. You have a 3x inside of a cosine, but you really don't need U substitution. Some of you may be able to realize that all you have to do is take the antiderivative of cosine, which is going to be sine. So let me work it out here without U substitution. I will do it with U substitution in just a moment. So let's see, that'll be sine of 3x. Now, if I take the derivative of sine of 3x, I should get cosine of 3x. So let's try that. Let me take the derivative of this function. If I take the derivative of sine of 3x, I'm going to get cosine of 3x But then because of chain rule, I'm going to have to multiply that by the derivative of the inside, which is 3. Well, that doesn't quite work out. I wasn't supposed to get 3 cosine of 3x. I just need for it to be cosine. So something I could do is to multiply it by 1/3. Kind of anticipate that 3. If I multiply this antiderivative by 1/3, I can see that my 3's are going to cancel. And that would give me cosine of 3x, which is exactly what I started with. So the antiderivative is not just, it's not just sine of 3x, it's going to be 1/3 sine of 3x. And then I would proceed with plugging in my boundaries, 0, pi halves first, and then 0, and getting an answer. And that's kind of how you do it if you can just do the antiderivative mentally. But I'm going to show you a method called U substitution that does the same thing in case you don't catch that 1/3 or if you're not able to get to the antiderivative. So let me erase these and show you how that works. Okay. So the first thing you're going to do is you have to pick a function to substitute for u. You always want to pick the function that is sort of in the most complicated position. So I have a cosine, and inside of it I have a 3x. So 3x is sort of in the most complicated position. So I'm going to come over here and I'm going to say that u is going to equal 3x. Okay, so if I were to rewrite this integral, the integral would now be cosine of u. And I'm going to go real slow, so hopefully this is not too confusing. So I said u is 3x, so 3x automatically becomes u, but now I have a dx. Now you're not allowed to take an integral of 2 different variables. These 2 things have to match, which means I need to figure out a way to get rid of dx. And I'm going to use my little equation, my u substitution setup here to do that. So what I'm going to do is I'm going to take the differential of both sides, not the derivative, the differential. If you remember, the differential is simply the derivative of the function, so in this case it would just be 1 times the times du or dx, whatever the name of the variable would be. So in this case it becomes 1 du. On the right side it becomes 3, the derivative of 3x is 3, and then we're going to multiply that by dx. And so that's how you take a differential. We're not taking a derivative, we're taking a differential, which is the derivative times dx or du, whatever the name of the function is. So what you're going to notice right away is that I have dx right here, but I don't really have dx here. I have 3 times dx. Now if I'm going to do a substitution, it needs to say dx. So what I'm going to do is divide by 3. So I'm going to get 1 over 3 du equals dx. And since now that's the same as this guy right here, so dx is the same as dx, I can now replace dx with whatever I know it's equal to, which is 1/3 du. Okay, so we're going to rewrite this integral. This is going to be the integral cosine of u, and instead of dx, I'm going to put in 1/3 du. Okay. Now, because of properties of integrals, I can take this constant, everything's multiplied, so actually I can take this constant and I can send it outside. So that's exactly what I'm going to do, just to make things a little bit nicer. So 1/3 comes outside. I don't have to do that, but it just makes it a little bit easier to work with. And then I have cosine of u times du. And now the variables match. Everything matches, everything's perfect. I still haven't taken an antiderivative, but it should be easier to take that antiderivative now that it's cosine of u as opposed to cosine of 3x. One more thing I have to keep in mind. The 0 and the pi halves were boundaries that applied to the function cosine of 3x. Since I've changed that function now, it's cosine of u, my boundaries have to reflect that change. So I'm going to go back to this u equals 3x, and I'm going to plug in my boundaries. First, pi halves. So u of pi halves, basically I take equals 3 instead of x, I replace with pi halves. and I'm going to get 3 pi halves. So that means that the boundary that used to be pi halves for my new integral for the u substitution one is now going to be 3 pi halves. Then I'm going to do the same thing with the lower boundary, 0. So u of 0 is going to equal 3 times 0, which is 0. So that means my lower boundary stays at 0. Okay, and now I'm ready to evaluate. I'm going to follow my fundamental theorem of calculus part 2. And I'm going to, my 1/3 is just there. I'm going to take the antiderivative, of cosine, which is sine. I'll write that here. So the antiderivative from 0 to 3 pi halves, let me write it out here. The antiderivative is going to be sine of u. I don't have to worry about 1/3 or anything because it's just u. So sine of u, if I take the derivative of sine of u, I get cosine of u, so I know I'm good. My 1/3 is sitting out here. So now it's going to be sine of 3 pi halves. Remember, I have to use my new boundaries. Minus sine of 0. Okay? And then whenever I evaluate this, I need to multiply by 1/3. So if you remember, 3 pi halves, that's in the unit circle, that's over here. So that's going to be, for sine, it's going to be -1. Okay, so 1/3. And then sine of 0 is just 0. So this one goes to -1. So in the end, I get -1/3. And that's my answer. So this process is a little tricky at first. You only really get good at it by doing many, many examples. So let me just kind of trace back my steps. I chose, first of all, the function that was in the most complicated position. In this case, it's 3x because it's inside of cosine. I let u equal 3x. Once I did that, I needed to find a way to get rid of dx. So what I did is take the differential of both sides, so that's the derivative times du, the derivative times dx, and then I got 1 du equals 3 dx. I then needed to match dx with dx, so I got rid of the 3 by dividing both sides by 3, and then I could replace dx with 1/3 du. Once I did that, I needed to make sure that I adjusted my boundaries, because now I'm in terms of u, I'm no longer in terms of x. And I did that by plugging in my old boundaries into my u function, because those were x's, and now I'm going to evaluate the u. So here's my new boundaries, 3 pi halves and 0. Then I proceeded to find the antiderivative, and that was just sine of u. And if you do the substitution right, this step should be easier than the original one. And then I went ahead and followed my fundamental theorem of calculus part 2, took the antiderivative, plugged my top boundary, plugged my bottom boundary, evaluate those. Don't forget about the 1/3, and I'm done. I'm going to go ahead and make 3 other videos regarding 3 other examples. I encourage you to watch them, and hopefully it will make more sense as you go along. See you soon.